Okay, so just a few quick things, reminders. Your quiz is currently open. It will stay open until 2:01 tomorrow. So you have until 2:01 p.m. on Friday to complete it. At that point, the quiz is closed. It stays inaccessible until I'm sure everything is in and graded, and then it'll become accessible again, which is usually like sometime later in the day on Friday or Saturday, somewhere along. Let's see. The content that we're going to go through today takes us through the second half of this chapter, this fifth chapter here in Intro. So we're right on pace with where we ought to be. This is like a more conceptual chapter, so there's not a ton of math that's involved in this chapter, which is good. We can use a little break from that, but we're going to get a Did anyone else get kicked off? I got my program closed and then open again. What the heck happened? It says it's still recording. What does the chat say? I'm freezing a lot. I'm going to switch networks. Hold on. I have a better network. This might do something for a second. Come on now. Switching networks, and it says my act. Okay. I'm connected to a better network now than normal. I'll admit, Alex. Anything better now? You guys able to hear me, see me? Is that okay? Yeah, okay, thanks. All right, so just to reiterate, quiz is due tomorrow at 2:01. Homework is due on Sunday at 11:59. Extra credit is due Friday at 11:59. We're going through the fifth chapter of Pro. Not a lot of math in this portion of the chapter, more conceptual stuff. And we'll get right back into the math when we get into gas laws and thermochemistry for the next 2 weeks. Next week is all gas laws, the one after that is thermochem. And then that takes us right up to our second exam before we get into like quantum stuff. And then that's a pretty big break from math. So we're approaching what I would usually refer to as peak math. All right, well, with that said, I'm going to go right into the presentation here now. It's still recording, that is good. I might come on to this again. So I'm going to start sharing my screen. Okay. So today's class, the 11th. First, I need to correct something from the past lecture. One of you, I won't call you out by name, but you know who you are, and thank you so much for your attentiveness, found an error in the previous lecture. And so I've gone through and corrected it here. I'll put the correction in the PowerPoint, and that'll get posted as well when I do my sort of late afternoon postings. But so that'll be corrected. That's the first thing I'm going to get to today. And then after that, we'll get into soluble ionic species, where we talk about the solubility rules, precipitation reactions, things that result in a net ionic reaction, acid-base reactions, and oxidation reactions. These are all just different applications of different kinds of reactions. So to correct the thing from the last lecture, there was this solution concentration challenge problem, where we had some solution that was made by dissolving a certain amount of silver sulfate to make 250 mils of solution. If 10 mils of that solution was diluted to a final volume of 75 mils, it was found that the concentration was 0.0025 molar. What mass of silver sulfate was dissolved? Well, you know, this is sort of what we do first. M1V1 equals M2V2. I have this concentration and this much of it. And I got that by taking 10 mils out of some more concentrated solution. So let's find out what the concentration there is. 0.01875 molar. That's exactly what it was last time we calculated it. And the way to find out how many moles there are is to multiply that by the volume of that solution. So that solution was a 250 milliliter solution. That's where that number comes from. And there are 2 moles of silver in every 1 mole of silver sulfate. And every mole of silver sulfate weighs 311.799 grams. We'll go through and do that. 0.731 is the answer that you should get. I had written down in the last one 2.91, and the reason I had that incorrect is because I neglected to put this number in my calculator. So, as a result, I had the wrong answer, but a student with the right answer wrote to me. Thank you very much. So, just to be clear, this is what we're looking for there. So that will correct that from the previous lecture. Thank you for bringing that up. Now, in any chemistry class, you will be exposed to the solubility rules, and this is no exception. So when an ionic, and solubility rules apply to ionic compounds. When an ionic compound is put into water, it tends to do one of two things, either sink down to the bottom like a stone, or it will ionize and break up and then sort of be dissolved. And so being soluble means ionizing for aqueous solutions. And so if something is an ionic solid and it's soluble, it breaks up into its cations and anions. Generically, that's some metal cation and some anion. Not necessarily a single nonmetal, could be polyatomic. This is a 2046 point, so this is one of these things that we introduce in this class, which has some truth to it, but not as completely true. This solubility chart right here is something that we hold on to, but every species that's mentioned on this chart has a limit to how soluble it is. It's all temperature dependent. So that's something we cover in 2046. So if you're one of those students who's going to go on to second semester Gen Chem, this will get revisited and revised. But there are some important things to remember. And please, if you're going to use charts to sort of remember the solubility rules, one, it's a good thing to do because you're less likely to get them wrong. And two, try to look at them in charts like this and not matching. So like matching a cation and an anion to find out if they're soluble or not. That is not a good way to go about and find out if something is soluble. We put these things into groups for a reason. So in large groups, all nitrates are soluble. So all nitrates, all acetates. If I have an anion that is a nitrate or an acetate, no matter what the cation is, that is a thing that will dissolve and ionize in water. All group 1 cations, so lithium on down and ammonium, no matter what the anion is, if I put that in water, it will dissolve, it will ionize and split up. Okay? So those are the things you want to pay attention to. Now there are others that are mostly soluble, like chlorides, bromides, iodides, those sorts of things. However, there are some exceptions. So all these chlorides, bromides, and iodides are soluble unless the cation is silver. So if I have silver chloride, that is not soluble. Silver bromide, not soluble. If it's mercury 1 or lead 2, these are also not soluble. So lead 2 iodide would not be soluble. Sulfates are soluble as well, except for when they are paired with strontium, barium, lead 2, silver, and calcium. So if any one of those is the cation that pairs with sulfate, it is not soluble. Okay, so magnesium sulfate, that will be soluble. Calcium sulfate would not be soluble. Generally speaking, most hydroxides are insoluble with the exceptions of things in group 1. Most sulfides are insoluble except for these that are soluble. Hydroxides are sort of marginally soluble. Carbonates and phosphates tend to be insoluble except for group 1. So you'd want to pay attention to these sorts of things. If you're working with a lot of, especially in environmental chemistry, the sources of ions are important. So a chart like this is really quite helpful. And if you use it enough, eventually you can sort of memorize it. So a precipitation reaction is when we take two solutions, homogeneous solutions, and we pour them together. And what we make is a new solution. And in that new solution, we form a precipitate. And that precipitate is something that is insoluble and literally falls to the bottom, so it looks like it precipitates out. So potassium iodide and lead 2 nitrate will form potassium iodide and, lead iodide, lead 2 iodide, and potassium nitrate. And notice that the phase here is solid while all the others are aqueous. So two solutions, these two things right here, are combined and they make these two things. This is the yellowish solid, and then this is an ion that's still in solution. And this kind of reaction, it's a general kind of reaction, it's known as a double displacement reaction, or partner switching type reaction. So I've labeled this cation as red and this cation as green, and this cation is going to switch anions with this one. So this potassium is going to get this nitrate. This lead is going to get this iodine. And when it does, it forms lead-2 iodide, and it just so happens that this is a solid and falls out of solution. This potassium nitrate is still soluble. And we're going to see what that means in a second. So you can see, like in the cartoon graphic here, we have potassium ions and lead ions in one solution. In this other solution, we have lead ions and nitrate ions, and then when they combine, the lead finds the iodines, and then they form a solid lead iodide that does not dissolve. And it's, as a demonstration, it's actually quite beautiful, but you end up having all the lead to deal with. And that is actually one thing worth saying. Why is this important? Well, if you remember the crisis that they had and kind of are still having in Michigan, where lead was in the drinking water, lead is a terrible thing to have in the drinking water. It can cause severe developmental delays in children. One of the options for getting lead out of the drinking water is sending something in that will capture it. So something like lead potassium iodide will form a complex with lead iodide to make lead iodide, and that will remove it from the water. It's the ionic lead that we're really kind of worried about. Once it's in its solid form, then we can sort of like scrape it off and dispose of it a little more responsibly. So things like this, a general chemistry 1 concept, is actually quite relevant in the problems of today in Michigan. So there are some expectations with double displacement reactions, things that you as a chemistry student would be expected to do. One is that if you are given a pair of reactants, you should be able to predict the products. So if you were told you have potassium iodide and lead-2 nitrate, you should be able to tell me what comes out of that. I shouldn't have to give you that second. What product, if any, of those is a precipitate? You should be able to determine that by looking at the solubility rules. You should be able to write the complete molecular equation, which is just sort of like the second half of this first thing here, and then write the net ionic equation, which is something we're going to get to right now. So here is this is a question that you would have on a quiz if you know, we're meeting face to face. So what are the products and the net ionic equation of this set of reactants? So when I do a problem like this, I actually like to write it out in terms of words. So if I have lead-2 nitrate and potassium chloride, in terms of words on the other side, I'm going to have lead-2 chloride and potassium nitrate. So the double displacement, I'm completing this reaction. So I'm trying to describe the steps over here. The reason I do this in words is because then I can turn this into a nomenclature exercise. And it makes sure that I don't change charges. So if I have lead with a +2 charge on this side, I also have lead with a +2 charge on this side. And then I can write that in terms of an equation. So I've got lead-2 nitrate here in red, and I've got potassium chloride here in green. And you can show you how they split up there. And you also notice that's probably not balanced, so I want to balance that equation. 2 potassiums, 2 potassiums, 2 chlorines, 2 chlorines. Lead's fine. So now it's balanced. And now I want to look at my solubility chart to see what's soluble and what's not. Typically speaking, everything on the left-hand side or the reactant side is soluble. One of these two things on the right-hand side is probably not soluble. And if I go through and look, I'd find all my chlorides are soluble except for silver, lead, and mercury 1. So this would be a solid. Everything else here is liquid, or aqueous. So I assign phases in this set. Next, I'm going to break things up. So the fact that I've got this here as aqueous means that this is ionized. So this is not floating around as lead-2 nitrate. It's floating around as lead nitrate, lead 2+ and 2 nitrates. Okay. Why 2 nitrates? Well, because every lead has a +2 charge, every nitrate has a -1 charge. So I have 2 nitrates for every 1 lead. And this little subscript 2 comes down and goes right there. Potassium and chloride. Okay, so that's how it breaks up. And I've got a 2 in front. That means I've got 2 potassiums and 2 chlorides. So this side over here, I just bring down my lead-2 chloride. It's a solid. It doesn't not ionize. So it just stays as is. And I've got 2 potassium nitrates, which means I have 2 potassiums and 2 nitrates. And they're all separate. Okay? So they're aqueous. Now, what I'm going to do is identify something called spectator ions. These are ions that appear on both sides of that reaction here, on the reactant side and on the product side. And because they're on both sides, that means they're not participating in the reaction because they're not changed in any way. And if they're not participating in the reaction, I can eliminate them from what we're going to call the net ionic equation. So if I draw a line through these, it means that they're they're not important. They're not participating. They are the Milwaukee Brewers of this, thing here. They're just there. No one cares. So, apologies to Brewers fans. So I've got a lead-2 compound here. I've got two chlorines here, and I've got lead-2 chloride. Those are the things I have not crossed out. So all I need to do is just maybe rewrite it. And generally speaking, especially if you're doing this in something like mastering, they want the phases. And so write the phases in to be clear. One thing that I want to be clear about, when I'm saying this is aqueous, lead-2 nitrate, it means that it exists as a couple of these ions. When I'm writing this is aqueous, it means it's dissolved. Okay, so there's no further way for me to split up this lead atom. So this is my net ionic equation. And then just to sort of like summarize the steps, I complete the balanced equation, so it looks like that. I assign phases, so it looks like that. I break up these ions, so it looks like that. I cancel out the spectator ions, and then I rewrite the remaining reaction, so it looks like this. If I've done this right, the only ions present should be the ones making the solid. So if I made PbCl2 solid, then the only ions present should be lead and chloride. Which means that I should be able to jump from this step here all the way down to this one by realizing, oh, that's my solid. That means I should just have lead and chlorine and everything else cancels out. So if you want to be able to, at least in terms of handwriting, skip a couple of steps, once you come to that realization, it's a fairly handy thing. Okay. And actually, as you advance in chemistry, that's a really good technique because you'll start to think of solutions not so much as what the identity on the bottle is, but in terms of the ions that are present. So you won't look at a potassium bromide solution as a potassium bromide solution. You look at it like, oh, that's my bromide source, or that's my potassium source. Okay. Questions on this? There's only like 4 of us here, so if you want to unmute yourself and ask any questions, it's totally fine. Okay. So another example of this same exact thing, write the molecular and ionic equation for the following set of reactants: sodium sulfate and ammonium chloride. So moving in here to something where I can handwrite. I've got sodium sulfate and ammonium chloride. It's going to make sodium chloride and ammonium sulfate. I wrote it out in words just because it's nice and easy for me to turn words into formulas. So Na2SO4 and 2 NH4Cl goes to 2 NaCl and NH2SO4. All right, so that's it. And I'm going to assign phases. They're all aqueous. Not a single one of those is insoluble. So when I break these up, all of those break up into their ions, 2 sodiums and a sulfate, and 2 ammoniums and 2 chlorides, and 2 sodiums, 2 chlorides, 2 ammoniums, and sulfate. And what I might notice is that every single one of them cancels out. So I've got a sulfate on both sides, ammonium, chlorine, sodium, they're all on both sides, which means that nothing's undergoing a change. The left-hand side looks just like the right-hand side. Maybe it's just written in a different order, but they all look the same. Which means that there is no reaction in a situation like this. It's not a reaction, it's mixing. So I put 2 things together and I have mixed them. I have not done a reaction. And so typically for something like this, you would, a lot of times mastering will say, write NR or leave no reaction. This is an example for a place to do that. Another kind of double displacement reaction is an acid-base reaction. Now, this is another one of those things that we introduced with some truth, but then we challenged that truth in second semester. So for those of you who are going on to 2046, acid-base reactions are something we spend like 2 weeks on. So acids are a species that produce hydrogen ions, or at least that's under one very specific definition of acids. And what you guys can think of, in this class at least, it's handy to think of an acid as something that's ionic, but the cation is H+. Okay, so HCl, HNO3, H2SO4, this has 2 H+. So each one of these is an acid, specifically a strong acid. Bases are species that produce OH in solution, again under one definition. So an ionic species where the cation is OH- is something that you can think of as a base. There are many other kinds of bases, but this is one that you can think of as a base. Right enough for now. Sodium hydroxide, potassium hydroxide, strontium hydroxide. This one has 2 OHs. So these are things that you can think of as acid-base reactions. And if we were to pour them together, one of the things you might notice is that we form water, H2O liquid, and sodium chloride. So we make a salt and water. And that's common for really any acid-base reaction. The two things you should make are a salt and water, usually a soluble salt and water. So that means that if I pour these two things together, I pour two clear liquids together, I make a clear liquid. It looks like nothing happened, but in fact, something really did happen. So that's why we use an indicator in titration, which is something we'll get to in a minute. So here's the general reaction. I've got an HCl solution, sodium hydroxide solution, and that makes more water and sodium chloride, which is soluble. So let's write the net ionic equation for something like that. So I've got HBr and sodium hydroxide. So I will combine them to make NaBr and HOH. Another way of looking at HOH is as H2O. So HBr and sodium hydroxide, those are both aqueous. Sodium bromide is aqueous, and H2O is not aqueous. Interestingly enough, water is not aqueous. Water is not water soluble. Water is water, it's a pure liquid. So when it comes down to it, I get to break these things up into their ions. So H plus and Br minus and Na plus and OH minus, and goes to make Na plus and Br minus and H2O. So the net ionic equation, once I identify and cancel out my spectator ions, is this: H plus and OH minus goes to make H2O. Not bad. So that is the net ionic equation for just about any acid-base reaction. Okay? A certain amount of H combines with a certain amount of OH to make H2O. That's an acid-base reaction. We use that to our advantage in what's called a titration. Typically, this would be a very fundamental lab that you would have done in 1025 lecture, 1025 lab. You would be doing it in 2045 lab as well. Excuse me. And in this titration, or any, incidentally, not all titrations are acid-base, but this one is, we use a known volume and concentration of a base to determine the unknown concentration of an acid. So that is, in this burette here, and that's what this thing is showing, I'm delivering a known volume of sodium hydroxide that I know the concentration of into a flask that contains a known volume of acid that I don't know the concentration of. So I'm using this as a known to find out something about this as an unknown. As I add this, my hydroxide solution ends up reacting with my water. So with the H plus that's in here to make water. And I also end up adding a couple drops of a indicator called phenolphthalein. It looks clear, usually add 2 or 3 drops. And then we titrate this until we see a pink color that is permanent, but very, very slight. And that's because when I add 1 drop of base that has no more acid to react with, that drop of base will react with my indicator. When it reacts with my indicator, that means that now I'm out of acid. So I want the slightest color so that I can be as close to running out of acid as possible. All right, so I think this is an experiment you guys are probably familiar with. Now, here's an example of a problem that we can expect with this. So a 30 ml sample of an unknown phosphoric acid solution is titrated with 0.1 molar sodium hydroxide. The equivalence point is reached when 26.38 mils of sodium hydroxide is added. So what is the concentration of H3PO4? And I should say this word here, equivalence point. The equivalence point is when the same number of moles of hydroxide is equal to the same number of moles of hydrogen ions. So that is when moles of OH equal to moles of H. That is what the equivalence point is. So I'm combining H3PO4 and sodium hydroxide, and I'm going to end up making sodium phosphate and water, and then once balanced, 3 of these and 3 of these. So the thing I can get moles from is my information on sodium hydroxide. I know the volume of it, and I know its concentration. So I know everything about this. I know some stuff about this, but not enough to get moles. So this is what I'm going to start with. So I've got a 0.1 molar solution of sodium hydroxide. I've got 0.02638 liters of it. So just converting that to liters. 3 moles of sodium hydroxide react with 1 mole of phosphoric acid. And then there were 0.3 liters of this there. So my liters will cancel with liters. Moles of sodium hydroxide cancel with moles of sodium hydroxide. I'm left with moles of this and liters of that on bottom, moles per liter. So that's going to be concentration. And I come out with 0.0293 molar phosphoric acid. Now, it's a fairly straightforward calculation. It is stoichiometry. I encourage you to think of it that way. If this is a 1-to-1 ratio, this can also be expressed as something like M1D1 equals M2D2. However, this is stoichiometry, so I do encourage you to think of it in terms of stoichiometry. The mole-to-mole ratio is important because it's not always 1-to-1. I have seen some students, get things wrong because they make that assumption. So always pay attention to your balanced chemical equation and realize that titration is a balanced chemical equation. The last kind of reaction that we have for today is oxidation reduction. In an oxidation reduction reaction, it's very different from the other kinds of reactions we've seen because electrons get exchanged. So if electrons end up getting exchanged, what that means is things change charge. So in this case, or in any case where a redox reaction is happening, and that's the shorthand way of discussing oxidation reduction, something's being oxidized, which means it's losing electrons. If something loses electrons, its charge goes up. It becomes more positive. It gives away negative things. Another atom is reduced, which means that it is taking in negative things, becoming more negative. And so its charge goes down. Here's an example of an oxidation reduction reaction happening without the presence of oxygen, which is fine. Sodium metal, which is it looks like bad butter. So if you have some sodium metal, it comes in these chunks, and you can actually slice it with a knife. And chlorine is a gas that you have no business breathing. So if I were to expose some sodium and chlorine in this little reaction vessel, what happens is it forms sodium chloride, actual salt. You can make your own salt this way. Now, this is not the way that salt is produced, large amounts at least. But this is a way to demonstrate that this is a redox reaction. So in order for us to figure out what a redox reaction is, we need to know some rules for assigning oxidation numbers. So your book gives a series of rules. I forget the number of the page that it's on, but these are basically those rules, more or less transcribed because they're a good set of rules. So the oxidation state, or charge, which is a decent way to think about it. The oxidation state for a free atom in its elemental state is 0. So if I have any atom just sort of by itself in its elemental state, like calcium solid, copper solid, nitrogen gas, which is diatomic, or oxygen gas, which is diatomic, and others, there are many, many others. Excuse me. Its charge, or its oxidation state is 0. That is just a by definition thing. Now, the oxidation state of a monoatomic atom is equal to its charge. And so if I've got a Ca+2, a calcium +2 ion, then its charge is +2. If I have a chloride anion, its charge is -1. So basically, this is a really easy one because we're basically telling you the charge of the thing is right next to the metal, or right next to the non-metal. That's what its charge is. For groups of atoms, the sum of oxidation states for all atoms in a neutral molecule is 0. Okay, so if I've got a neutral molecule, like sodium chloride, the sum of all charges here adds up to 0. So the charge on sodium is +1, the charge on chlorine is -1, the sum is 0. That's what should happen for a neutral molecule. For an ion, the sum of all oxidation states is equal to the charge of that ion. So sulfur, whatever its charge is, plus 4 oxygens, whatever those charges are, add up to a total of -2. That helps us figure out what the charges of some things are. I've got an exercise to show you that in the next slide. A couple things are given. So for example, for the metals, group 1, that first group on the periodic table, they will always have a charge of +1. Group 2 metals will always have a charge of +2. Other in compounds, there's a table that's used. So fluorine will always have a charge of -1. Hydrogen will always have a charge of +1. Oxygen will always have a charge of -2. Then most group 7A, for things like chlorine, will be -2. Group 2A, usually sulfur will be -2. Group 5A, usually -3. The important part is that the top portion of this takes precedent of the bottom portion of this. I'll explain what that means in a second. If you understand rules for how we can assign charges to metals and nonmetals, it's easy for us to figure out what the oxidation number of something is, because that's what we have to pay attention to in a chemical reaction if things are going to change. So, we have two things we want to determine the oxidation state of. First, what's the oxidation state of sulfur in sulfite? So this is sulfite, SO3 2-. I want to figure out what the charge of sulfur is. So that means whatever the charge of sulfur is, plus 3 times whatever the charge of oxygen is -2. Oxygen has a charge of -2. So whatever the charge of sulfur is, plus 3 times -2 equals -2. This must be +4. Okay, so 4 minus 6 is -2. So the charge of sulfur in sulfite is -2. What's the oxidation state of chrome, of Cr, and potassium dichromate? This is potassium dichromate, K2Cr2O7. So 2 times the charge of potassium plus 2 times the charge of potassium plus 2 times the charge of chromium plus 7 times the charge of oxygen adds up to 0. There's no net charge on this. Dichromate has a charge, so does potassium, and together there is no net charge on this thing. Potassium has a charge of +1. Chromium is the one I want to figure out, so I'm leaving that as a variable, and oxygen has a charge of -2. 2 times +1 plus 2 times my variable plus 7 times -1 is 0. So just bunching things up. 2 times chromium -12, -14 plus 2 is 0. Chromium must be 6. So the charge of chromium in potassium dichromate is 6. Now, what we can do is we can use this in what's known as a redox reaction. That is, we'll put two things together and see how they react based on the way they change charge. Here is a well-known reaction. Zinc plus iron ions, iron plus 2 ions, goes to make zinc plus 2 and iron solid. So basically one metal would dissolve and one metal would form. My goal is to identify what's being oxidized and what's being reduced. So I introduced oxidation and reduction a couple of slides ago. Zinc is going from a charge of 0 on this side because it's an element and it's free. It's an atom in its elemental state. To zinc with a +2 charge. This charge over here says it's +2, so it goes from 0 to +2. The way it's doing that is by being oxidized. It loses 2 electrons. Iron has a charge of +2, and it's going to iron with the charge of 0. So on this side, it's charged at +2. On this side, it's an atom in its elemental state, so it's charged 0. That means iron is being reduced. And in every redox reaction, one thing is being oxidized and one thing is being reduced. You never have just one. So the other thing we sort of want to point out here are what's called oxidizing and reducing agents. Right, so the oxidizing and reducing agents, these are the way that we actually store and refer to these kinds of species. So some species that is being oxidized, so in this case, zinc is oxidized. Zinc is acting as the reducing agent. And why is that? Well, zinc is giving its electrons to iron. So if zinc is being oxidized, electrons are being lost from it. That means its electrons are actually being given to something else. So zinc is reducing iron in this case. The species that's being reduced is an oxidizing agent. Okay, so whatever is, having its charge going down is taking electrons away from something else. So iron 2 plus is taking electrons from zinc. So iron 2 plus goes to iron 0. That does so by gaining 2 electrons. So it's taking its electrons from zinc to do that. So that makes it deoxidizing. So for reactions like this, you would be expected to find what's being reduced, what's being oxidized, what's the oxidizing agent, and what's the reducing agent. And what I can tell you is that you need both sides of this to solve it. However, your answer, all of those questions should only come from things on the left-hand side. Once things are on the right-hand side in products, they are no longer being oxidized or reduced. They are oxidized or reduced. All the answers that we come up with for this question are always on the left-hand side. So here's the question. 4 lithiums plus oxygen goes to make 2 Li2O. Right, nice little balanced equation here. Question is, what is being oxidized? What is being reduced? What is the oxidizing agent? What is the reducing agent? So let's take a look at the solution here. Lithium is going from a charge of 0, it's an atom here in its elemental state, to a charge of +1 on this side. So its charge is going up, it must be losing an electron. Oxygen is going from a charge of 0, here it's an atom in its elemental state, to a charge of -2. So it means it's gaining electrons. These two numbers do not have to be equal, by the way. So what's being oxidized? Lithium is, because its charge is going up. What's being reduced? Oxygen is, charge is going down. That's the easiest thing for us to find. So whatever is being oxidized is the reducing agent. Whatever is being reduced is the oxidizing agent. The oxidizing agent is different from what's being reduced in the sense that it's the entire species. So the oxidizing agent is O2, whereas the atom being reduced is just straight up oxygen. So it's something I always correct students on, but something you want to be cognizant of. Oxidizing agents are entire species. Atoms being oxidized or reduced are just one atom. And so if lithium is being oxidized, that makes it the reducing agent, and so it's the reducing agent. And just lithium by itself on the side. We wouldn't say 4 lithium, because it's just lithium. 4 is the number of moles that's being used. Okay? So, like I said before, there's not a lot of math in this portion. It's mostly just about like realizing what goes into and comes out of different reactions. That takes us out of that material. So, what questions do you guys have, if any, on what we saw there? Anything? Okay, so if there's no questions, some things to remind you on. Quiz closes at 2:01 p.m. tomorrow, so please make sure you get it done before then. Extra credit due Friday, 11:59. Homework due Sunday at 11:59. Next week, we'll start our work on gas laws. Okay, so you're going to want to, you're definitely going to, if you're not in the habit of reading the book now, you should be in the habit of reading the book from chapter 6 forward. That actually becomes a very important one. So we're going to want to pay attention to that. Let's see here. Danny's got a question here. A2 plus 2B1 minus. B2 plus 2A1 minus. If a reaction occurs. You're talking about the, so Danny's got a question about the activity series, which is something that I do not really go over in this class. There's not much on it. So let's see here. If I got A2 plus 2B minus goes to that, that means yeah, A2 is more active than B. The reaction does not occur, that means B2 is more active than A2. Danny, if you want, I can talk with you about this like after class because it's not on this stuff. Okay. So I'm going to stop my recording. And you guys have a good one. And Danny, if you want to hang out, we can talk through it.